Okay, we'll start now. In last class, we have seen what is meant by circular doubly linked list and the different operations which can be performed on circular doubly linked list. And we have just gone through how to represent a stack using a doubly linked list, and also how to represent a queue using a doubly linked list. Now, the next concept we are going to discuss is polynomial representation using a linked list. Okay, now how we are going to represent polynomial using linked list, that we are going to discuss it. Now, in the first module, hello, Rupesh, mute your mic. In first module, we have seen how to represent this polynomial. There we have seen two approaches, that is by using a structure containing array, and the second approach was array of structures. These two approaches we have used to represent a polynomial, and here we are going to represent a polynomial using a linked list. Now you know what is meant by polynomial. Polynomial is a set of collection of terms where each term is going to consist of three components. Those are coefficient, exponent, and the variable. These are the three components of each term, and polynomial is nothing but a sum of these terms. Now, to represent a polynomial using a linked list, we are going to represent each term of a polynomial as a node of your linked list. Okay, now here we are going to, just a second, here we are going to represent every term of a polynomial as a node, and this is a structure which is used to represent a node of a linked list which represents your polynomial, and each node is going to represent a single term. Now to represent a term, these are the variables which you require: the coefficient as well as exponent. The coefficient represents the coefficient of that particular term, exponent represents the exponent of that particular term, and we have a pointer to the next term of that particular polynomial. Now this link is going to point at the next term of that particular polynomial. This is how we can represent a term of a particular polynomial using a node inside your linked list. Okay, this is the node structure with three variables: int coefficient, int exponent, and a pointer called a link, which is always pointing at the next term of a particular polynomial. If you don't have the next term, at that case, this link is going to point at the null value. Now, this is the global declaration where we have type defined this node to a node pointer, that is type def struct node star node. Then you have created two pointers of type node, means these are used to represent the polynomials. First polynomial is represented by a, and the second polynomial is represented by b. A points to the first polynomial's first term, b points to the second polynomial's first term. Now let us consider an example, and we'll see how to represent the particular polynomial using a linked list. Now this is an example polynomial. A is equals to 25x raised to 4 plus 12x raised to 2 plus 2x plus 7. Now how many terms are present in this polynomial? 1, 2, 3, 4 terms. Means in your linked list you are going to define 4 nodes, and each node is used to represent a single term of this polynomial. Now this term 25x raised to 4 is represented by one node, that is the first node. Now in this node, its coefficient is 25 and its exponent is 4. Now the link part is going to point at the next term of that particular polynomial. Now the next term is represented by this node, its exponent is 2 and coefficient is 12. Now this first term's link part is going to contain the address of second term. And similarly, the second term's link part is going to contain the address of third term. Now this is the status of third term. Its coefficient is 2 and its exponent is 1. It should be replaced with 1. And then its link part is going to contain the address of the fourth term, that is 7. Now here the coefficient is 7 and exponent here x is not present, means exponent is a 0 here, x raised to 0. This is how we can represent a polynomial using a linked list. Each term is going to be represented as a node, and node is going to have a pointer called link, which is always pointing at the next term of your polynomial. Similarly, you take one more example. It is b is equals to 28x raised to 5 plus 6. Can be represented as like this. 20. The first term's coefficient is 28, exponent is 5. Second term's coefficient is 6, exponent is 0. And if you see the link part of the last term, which are initialized to null, this diagonal line indicates that this value is initialized to null. This is how we can represent a polynomial using a linked list. By using a node structure like this, you can represent an individual term of a polynomial in a linked list node. Now, next thing, the different operations which can be performed on the polynomial. Now, these are the different operations which can be performed on polynomial. That is creation of polynomial. Second one is representing the polynomial or displaying the polynomial. Then the third operation is addition of two polynomials, and fourth operation also you can perform, that is multiplication of two polynomials. These are the possible operations which can be performed on polynomial. Now let us study these operations one by one. Right now we have seen how to represent a polynomial using linked list. Now on the same polynomial we are going to perform these operations, that is creation of polynomial. Now the creation of polynomial is same as that of your creating a new node in a singly linked list. Now what are the steps for creating a new node in a singly linked list? First of all, you are going to allocate the memory for that is by using malloc. Then you are going to store the data. Now in this case you are going to allocate the memory for a new term of a polynomial. The first dynamically allocate the memory for new term of polynomial, then store the coefficient and exponent value, that is power of x, in the term, then link the term to the previous term of the polynomial list. Link the term to the previous term of a polynomial list, and finally read the node of a polynomial as a term of polynomial. Now this is how we can create a polynomial. Now let us have a C function called a read, which is used to create a term of a polynomial. Now this is a function called read, which is used to read and initialize a term of a polynomial. Now these are the temporary variables which are required: the coefficient to store the coefficient of a term, x power to store the exponent, and n. Then you just create a pointer called start and initialize it to null, because initially the polynomial is going to be empty, and one more pointer, that is t, which is a temporary pointer which is used to iterate through the different terms of a polynomial. Then you ask the user to enter the number of terms. Enter the number of terms, scan it in n. Now means this n is nothing but total number of terms in a particular polynomial, means those many number of terms you are going to add in this particular polynomial. Then you are going to perform the addition operation these many of times, that is for I is equals to 0, I is less than n, I plus plus. Okay. Then For each term, ask the user to enter a term in terms of coefficient and x power. In terms of coefficient and x power. Now you read these two values in coefficient and x power variables. Then you store these values in t dot coefficient and t dot x power. That is, t dot coefficient is equals to coefficient, t dot x power is equals to x power, and then you just initialize t dot link is equals to null. Just initialize t dot link is equals to null. After that, at the you need to make the start to point at the first node. For that, what we will do, start is equals to attach t comma start. Now this attach function is going to attach a term t at the beginning of your polynomial. It is going to attach a term t at the beginning of your start. Now this attach function is written, attach is implemented as a separate function that we are going to discuss. Start is equals to attach t comma start, and finally you are going to return the new start of your particular polynomial. This is how we can create a new polynomial in terms of linked list. Okay, now this is an attach function which is used to attach a term in a given polynomial. Now this is how it works. Node attach t comma start. Now its return type is node. It is going to return the node pointer, which is nothing but the start pointer of the particular polynomial. Now it takes two parameters, the t, the node to be added, and a start. Now node, these are the two temporary pointers, temp and current. Now for temp, it is going to allocate the memory. Temp is equals to struct node star malloc struct node. Then temp arrow coefficient is equals to t dot coefficient. Temp arrow exponent is equals to t dot exponent, and temp arrow link is equals to null. Now this is a new term which is created. After creating, we just check whether the polynomial is empty or not. How to check it? If start is equals to null, means what? Your polynomial is empty. Whatever the term you are going to insert, that will be the first term. Hence you return temp, means this temp will be the starting node. Otherwise, you just assign current is equals to node. Start means you need to move to the last node of a particular last term of your particular polynomial. After the last term, the new term has to be inserted. That's why current is equals to start, while current arrow link is not equal to null. You move the current to the next link. That is, after completing this while loop, where this current is going to be placed at the last term of your polynomial. Now you just assign current arrow link is equals to temp. Now temp is the new term which is to be inserted, and you return the new start position of your polynomial. This is how this attach function works. Now this is an example shown here. Initially you have one term 25 and 5, means this is 25x raised to 5. Then I have added a one term, second term, that is 5x raised to 3. Now if I try to attach another term, where it has to be attached after this last term. Now to attach a new term after this last term, I need to place a pointer, one pointer here, that is current, and one more pointer I require that has to be point at the new node to be inserted. After that, this is how the term is going to be attached. 25 5 5 3 5 2. Now this is minus 5 because here it is coefficient is minus 5. The polynomial will be listed, will be given like this: 25x raised to 5 plus 5x raised to 3 minus 5x raised to 2. This is how we can create a polynomial, or how we can read the polynomial. Now the second operation which can be performed on a polynomial is representing a polynomial or displaying a polynomial. Now, for example, consider this polynomial a is equals to 25x raised to 5 plus 5x cubed, a polynomial which can be represented like this: 25x cap symbol which indicates raised to symbol plus 5x cap 3. And when we display a polynomial which is stored in a computer memory, it can be displayed as above representation. Now the following is the function that is going to display your polynomial in the above format. Now display function which takes the parameter, that is start node of your polynomial. First of all, before displaying, we just check whether polynomial contains any nodes or not. Okay, if it doesn't contain any nodes, means it is an empty polynomial. For that, this is the condition which we should check. Start is equals to null, means the polynomial is empty. We just display a message saying polynomial not created. And then we take one temporary pointer, that is temp is equals to start, and you have to iterate through all the terms of a particular polynomial. While temp is not equal to null, display each node, that is printf percentage d x, then raised to symbol again percentage d. Now this percentage d is going to be replaced by temp arrow coefficient, means in place of this percentage d the coefficient is going to be displayed, and then x raised to symbol, then the percentage d is going to be replaced with temp arrow x power, that is nothing but export. In this format the polynomial term is going to be displayed, and here the plus symbol is going to be displayed at the end of each term, that is then finally you move the temp to the temp arrow link, and the temp, it is going to print all the nodes of a particular polynomial until temp reaches a null value. This is how we can display the contents of a polynomial in this particular format. It is 25x raised to 5 plus 5x raised to 3. Now the next operation which can be performed on polynomial is addition of two polynomials. And in first module I think we have discussed about the rules to add the polynomials. To add two polynomials, we have discussed some rules, that is if the power of x is same for the term in polynomial a and in polynomial b, then we are going to add the coefficient and term is going to be attached. If the power of x is different in polynomial a, then we are going to attach the term to resulting polynomial. If the power of x is different in polynomial b, then we are going to attach the term to the resulting polynomial directly without finding out the sum. Okay, these are the three rules we should follow for polynomial addition. If the power of x is same in that both the terms, in that case only we are going to add the coefficient. If the power is not same in both the polynomials, in that case we are just going to add the term in the resulting polynomial as it is. Now consider the following polynomials a and b, and some polynomial can be obtained by the above rules. Now these are the two polynomials. A is equals to 25x raised to 4, 12x raised to 2, 2x plus 7, and b is equals to 28x raised to 5 plus 6. Okay, these are the two terms. Now how to find out the sum? First we'll compare the exponents of the first terms. Now here the exponent is 4, here it is 5, means both are not equal. In that case we are going to add these terms as it is. First we'll add the term with the highest exponent, that is 28x raised to 5. Then the next term 25x raised to 4. Next you compare the terms exponent of the next terms. Here the exponent is 2, here exponent is 0. Next we add this 12x raised to 2 first. Then you compare the exponent of this and exponent of this. Exponent of this is 1, exponent of this is 0. Hence what we'll do, we'll add this term 2x here. And then you compare the exponent of 6 and exponent of 7. Exponent of 7 is 0, exponent of 6 is 0. In that case we need to find out the sum of these coefficient, that is 7 plus 6 13, and add a new term with that coefficient with the exponent as any one of these two terms, 13x raised to 0. This is how we can add the two polynomials by using these three rules. Now the same by using same rules we are going to write a C function which is going to add the two polynomials. Okay, now this is and C function which is used to add two polynomials. Now this add poly function is going to return a pointer to a new polynomial, that is nothing but a resulting polynomial, and it takes two pointers, a pointer to a polynomial a and a pointer to polynomial b. Then you define a sum pointer called sum, which is nothing but the which is going to store the result of addition, that is initially it is initialized to null. And then you are going to construct a while loop while a is not equal to null and b is not equal to null until both the polynomials become null, means all the terms are added. This loop is going to be continued. Okay. Now first, what the first rule says, if a arrow x power is equals to b arrow x power, in terms if the exponents of the both the terms are same, in that case what you are going to do, you are going to add the coefficient, that is coefficient is equals to a arrow coefficient plus b arrow coefficient. And then after adding the coefficient, if the coefficient is not equal to 0, if the coefficient is not equal to 0, you are going to attach a new term with the coefficient and the exponent either of a or b. Here they have taken a's exponent, a raised to a arrow x power and the sum, where this term is going to be added to this new polynomial called sum. Then you move the a and b to the next term. A is equals to a arrow link, b is equals to b arrow link. Else if means the first rule is not satisfied, go to the second rule. Else if a arrow x power is greater than b arrow x power, means a's exponent is greater than b's exponent. In that case just attach a new term to the sum, a arrow coefficient, means a's term you are going to attach to the new sum polynomial, that is a arrow coefficient comma a arrow x power to this sum polynomial, and then you move the a polynomial to the next term. Okay, both the conditions, both the rules are not satisfied, go to the third rule. In that case attach a new term, that is b arrow coefficient comma b arrow x power to the sum, and move the b pointer to the next term, that is b is equals to b arrow link. This is end of else. Now after completing, just check for whether any nodes are remaining in these a and b polynomials. For that these two while loops are set up. While a is not equal to null, attach all the remaining terms to the sum polynomial, that is a arrow coefficient comma a arrow x power to sum, a is equals to a arrow link. Similarly attach all the remaining terms of b polynomial to the sum polynomial, that is sum is equals to attach b arrow coefficient comma b arrow x power comma sum, and move the b to the next term. B is equals to b arrow. Okay, finally we are going to return the sum to the calling function. This is how we can add the two polynomials using linked list representation. Okay, more about this we are going to discuss in your lab session, because your ninth program is based on addition of two polynomials. Now here you have taken only one variable in these two polynomials. You have only one variable called x, but in your lab experiments we need to solve the same problem with three variables. Here instead of x we are going to have three different variables, either x, y, z or abc, and each variable is going to have a separate exponent. That program we are going to discuss in our lab session. This is about polynomial representation and the different operations which can be performed on polynomial. Okay, the last point in this chapter or in this module is remaining, that is uh, representation of sparse matrix using a linked list. Now for representing a sparse matrix we are going to use uh, circular singly linked list, a set of circular singly list, and that we are going to discuss in next class. If you have any doubts of representing a polynomial using a linked list, you can ask.